So Unit 4, this is the final unit. It looks like our unit exam in this unit is probably going to be the Thursday or the Friday of the week we get back. Okay, and that will give us then 3 or 4 days of year review, and then we will write an in-class exam to replace your lowest unit exam mark, and then we'll have a day or two for year review to get you ready for the final exam. So this is called oscillatory motion and mechanical waves. The reason why we study what's called simple harmonic motion or oscillatory motion, which we're going to just touch on today, is because in order to explain waves, we need to understand that a wave, whatever that is, you have a general idea of what it is just a bunch of simple harmonic oscillators. So, for example, if I take a look at something like a cork that is moving up and down in water, that cork is experiencing what we call simple harmonic oscillation. But if I were to put that cork a little bit to the left of where it is, it's also going to be experiencing simple harmonic motion. But if I get a whole bunch of corks together, all experiencing that bobbing up and down, that simple harmonic motion, as long as they're not all bobbing up and down at the same time, but they're slightly out of sync, that's going to create what we call a wave. So when you look at a water wave and you see that ripple and you just kind of start dozing off on the beach and you see a wave, quote, going by, you see the crest of that wave moving, it's not. The water is not moving in that direction. What's happening is the water is moving up and down, giving you an illusion of something moving to the right. So that's why we tie these two ideas together. The picture you're looking at on the left is a jet breaking the sound barrier. And breaking the sound barrier means that the sound waves it's creating that are moving away from the front of the jet are moving away from the front of the jet at a certain speed, about 340 meters per second. So if the jet happens to fly at 320 meters per second, those sound waves start getting crowded towards the front of the jet. And as soon as the jet is moving at the speed of sound, it's moving at the speed of sound and it's creating sound waves in front of it that are just piling up on top of each other. And you hear what's called a sonic boom. Has anybody ever heard a sonic boom? I'll bet you have. Thunder is a sonic boom. It's something traveling at a certain speed that breaks the sound barrier. But if you have heard a sonic boom with a jet, it's quite loud, like it rattles your house. The picture on the right deals with what's called resonance. This is actually a thing. I know that, in movies they jazz it up and they say that you can, with the right voice, you can strike a note in your singing to shatter a glass. I don't know that any human being can actually do it, but you can generate, and forgive me for hurting your ears a little bit here, you can generate sounds which, does that bother you? How about that? I have a parking lot outside my house that teenagers kind of congregate in sometimes on Saturday night. And I hook that up with my Bose speakers and I open my windows and they leave pretty quickly. No, I don't do that. But if you generate the right frequency of sound, you can actually shatter the glass. And there's a video when we talk about resonance that I will show you that as the sound volume goes up, you can see the wine glass actually start to vibrate. And that's called resonance, when you have one object that is capable of vibrating with a particular frequency, anything nearby vibrating with that frequency will also cause that to happen. We'll talk in detail about this. Are you okay back there with your ears? We'll talk in detail about this later, but a couple of quick examples later when we study resonance. When I taught in Stettler a very long time ago, I was in my classroom one afternoon, there was an exam being written, and I could hear this noise, this whoo, 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 and it just kept getting louder and louder and louder. And the students didn't pay any attention to it, and I was wondering what it was. And afterwards I asked them, and they said, oh, well, that's the uprights on the football field. You know, the uprights on the end of a football field? When a train goes through town in Stettler, it vibrates the tracks when the train is moving at a certain speed, which vibrates the ground, and it turns out that those uprights had a natural frequency of vibration that matched that. And they would start vibrating, creating almost like a tuning fork, this sound. I had an old 1990 Tempo that at about 105 kilometers per hour, the frequency of the engine resonated with my whole car. If I was traveling at 104 kilometers per hour, it was the smoothest ride in the world. 106, smoothest ride. If I hit 105, the dash would start bouncing up and down, and the seats would start vibrating, and the steering wheel would start moving. So there was some natural frequency, and that's called a resonant frequency. And if you get close to the resonant frequency of a wine glass and then you go past it, you cause too much stress on the glass. Another example of resonance is just a cartoon. Somebody's working at their desk and everything on their desk is vibrating, and it's because the person next to them is jiggling their leg up and down. And, you know, what we're saying is that the stuff on this person's desk is capable of vibrating at the same rate as the person's leg. And that doesn't always work. You can't shake something and expect everything on the table to shake. But some things, based on their structure, how they're built, end up shaking very readily or very rapidly. So that's what that cartoon is about. All we're doing today is we are looking at a very basic introduction to simple harmonic motion, and the physics involved here is basically stuff you already know. It's very closely connected to circular motion. So we're going to describe simple harmonic oscillation. We are going to explain simple harmonic oscillation as a result of a force involved. It's called a restoring force. And then we're going to be working with period and frequency. And I say as it relates to simple harmonic motion because you already know how to work with period and frequency as it relates to circular motion. This is just a little bit different. So simple harmonic motion is any motion that's repetitive with a constant time of repetition. And that's key. It isn't some kind of random motion. It has to be in some way a back and forth motion, an up and down motion, a to and fro motion, but the time it takes to go through one complete cycle must be the same. So if you had, well, we'll look at some examples in a second, but that's key. So if you have a pendulum, and a pendulum is swinging back and forth, if it takes 1 second to go from one side to the other and back, and you come back later and it's still taking 1 second, then that's simple harmonic motion. If the period of time is not the same over time, then it's not simple harmonic motion. So the time it takes for a simple harmonic oscillator to complete one full cycle of its motion is called the period. Circular motion, uniform circular motion, is an example of simple harmonic motion. So is a pendulum swinging back and forth. So is a mass oscillating up and down on a hanging spring. And those last two examples we're going to study in detail. List a few quick examples of simple harmonic oscillators that we can think of. So, I mean, I've already talked about a pendulum. We can list a pendulum. And if I were to estimate the period of oscillation, that's a difficult task. And I don't have the big pendulum set up here, and we will set it up again when we have a lesson on pendula. But I think you might have a visual memory here of me pulling that rope so the bob of the pendulum is very close to the ceiling, and it went back and forth very quickly. But when the rope was very long, it took a long time for the pendulum to go back and forth once. And the time it takes for the pendulum to go back and forth once is called the period. So I don't think we should really estimate the period here, but we should make a note that the period depends on the length of the pendulum. And it's not a direct proportionality. You might expect that if you have twice the length, it's twice the period. It's not. Okay? The mass on a spring. Your memory of this will probably be more vague. But when we did the lab on Hooke's law, I had a spring here, and I had a mass on it. And we talked about in that lab the necessity of you keeping the mass constant. And then I pulled the mass down, and I let it go, and it was bobbing up and down. And I believe what I did is I said something about, well, that's going to be something we will study in detail later, that there's a certain kind of frequency or period to this oscillation. And then I believe I put a larger mass on it, and I got it to bob up and down. But when I had a larger mass, it took a longer time. And don't worry about how much the spring stretches. That's not the point. The point is the period depends on the mass. Now, only because this is such a short lesson, and I think I can help you out for later lessons, let's stop and talk about these two things for a second. What else do you think the period of the pendulum depends on? And this is a difficult question to answer, because you're probably not going to think of it. Let's walk away from that for a second. What else do you think the period of a mass oscillating on a spring depends on? If I hung a mass from the ceiling and hung it on a spring, and I set it in motion and I measured the period, the time it takes the mass to go down to the bottom, back to the top, down to the bottom, a full oscillation, what could I change to get a different period other than changing the mass? Noah? I could change the spring. So also, you can put here, and the spring constant, right? And I don't know if this makes sense to you or not intuitively, but if you had a very small spring constant, which means it's easy to stretch, the period would be longer. Would take a longer time, because the mass on the spring would be going way down, way up. And all of these things I'm describing with my hands, we're going to be doing on the lesson on springs, either Thursday or Friday. So I'm going to go back now and say, well, what could you change that would change the period of the pendulum? And the way I've worded it, I've kind of set you up for failure, so I won't word it that way. What else do you think the period of the pendulum depends on other than the length of the pendulum?
The pendulum itself? Like the mass of the pendulum, it swings?
Turns out no, surprisingly. But it's kind of, we're kind of along the right track. So one of the things we will look at in the lesson on pendula is we will change the mass, and we will discover that if you have a certain length and you change the mass, it's still the same period. Can I ask you a question? Why would you think it's the mass? Because this might lead us to the answer.
I just compared the two and kind of, I thought that if it's heavier, it would move longer.
So if it's heavier, that's good. Heavier has little to do with mass. It has to do with what?
Gravity.
The force of gravity. So you automatically say if you have more mass, you have a greater force of gravity. But it turns out that doesn't affect the pendulum. What will affect the pendulum's period is G. If we could dial up G to a stronger gravitational field strength, then it would be quicker. So the period of a pendulum on top of Mount Everest is longer than the period of a pendulum on the surface at the base. So also G. And this is why I had said, when I asked you what could you change I kind of set you up for failure here because you can't change g really very easily. But it is related to the acceleration due to gravity or the gravitational field strength. What are some examples of things other than, the physics aspect, a pendulum, a mass on a spring? Well, anything that is repetitive. So a piston in an engine. I mean, even if you have very little knowledge of mechanics, generally speaking, you have a number of pistons in an engine. You might have 8 pistons or 6 pistons. You might have a 4-piston vehicle. And each of those pistons is firing at a slightly different rate, not different rate, at a slightly different time, and they're collectively working together to drive the drive shaft and move the vehicle. But each piston is just a cylindrical piece of metal connected to a rod, and it moves in and out of the borehole. And it goes very, very fast. When you're driving a vehicle, if you have a vehicle that shows RPM, that's what we're talking about. So when we're hitting 4,000 RPM, those pistons are going in and out of those holes 4,000 times per second. It's not 4,000 revolutions per second. Your wheels are not going around 4,000 times per second. That's not what it is. It has to do with the engine. So, you could be talking here about the period being, well, the period is the time. So this is good. If the piston goes back and forth, say 1,000 times per second, that 1,000 times per second, I guess it's not too early to say this, is a frequency, isn't it? It's not a circular frequency, it's a frequency. And you know that period is 1 over frequency. I feel as though I'm confident on that, but can you confirm that 1 over 1,000 is 0.001 seconds? Pretty sure. So that's the period. If you're, this might be an idling speed or a very low speed that you're traveling at. I know this isn't perfect, but hummingbird wings. The hummingbird is just doing its best to maintain that frequency. It's not going to necessarily be a constant period, but this period of time will be very small. Right? I don't know that we really need to put a number on it. Is a record album, and I know that you didn't grow up with record albums, but you know what I'm talking about, right? Like I think it wouldn't be one of those cases like where you show 10-year-olds a dial phone and they don't know what to do with it. If I showed you a record player and a record, you could probably figure out what's happening, right? I hope. So when that record is turning around, it's turning around maybe at about this rate. 1/1000, 2 maybe 2 seconds for a period. It depends on the type of album. A 33 1/3 RPM is actually, I think, 1.8 seconds. A 45 is a smaller time. But you get an idea of what we're talking about here. This is just a basic introduction to get you used to thinking of things that are repetitive and regular as being called simple harmonic oscillators or simple harmonic motion. Now we need to go through a few definitions, and then we will take a look at a couple of examples today. What is the equilibrium position of a simple harmonic oscillator, or the equilibrium position of a wave, which we're going to get to in a week or two? Well, the equilibrium position is the state when no motion or energy is present. Okay, so you understand that if I take a tank of water, I can create waves. Take a tank of water, take this remote control, dip it in and out of the water, and I'm going to create a wave that travels away from this remote control. The equilibrium position of the water is what the water looks like when there's no wave in it. The equilibrium position of a pendulum is what the pendulum looks like, or where the pendulum is, if it's not in motion. It'll be hanging straight down vertically. When I hang a mass on a spring, and when you did Hooke's law, that lab, and you had it perfectly stationary, that's the equilibrium position of that simple harmonic oscillator, because it's not moving. When I tap that mass and it goes up and down regularly, the equilibrium position is where it was when it was not moving. Okay? And I hate to personify physical things, but what the equilibrium position is where the material wants to go to. So if I have a pendulum, and again, you're doing labs with this later. I didn't set them up today. If, my head is the pendulum bob and it's just hanging there, that's the equilibrium position. You don't have to imagine me as being just the head, okay? So you have some object here that is the pendulum bob. That's the equilibrium position. When the pendulum is in motion, it's swinging back and forth. When it's over here, it's trying to get back to the middle. Again, I don't mean to personify it, but there's some force involved pushing it in that direction. When it's over here, there's also a force pushing it in that direction, but it's probably a little bit less. When it's way over here, there's a force pushing it back in that direction. Do you have a question?
I don't want to say anything wrong, but would this be when that force is equal to 0?
That's exactly what it is. At that point in time, when it's at the equilibrium position, that force, which we're going to call the restoring force, is 0. And the further away the object, whether it's a mass on a spring or a pendulum bob or a piece of water that's way up top, the further away it is from that equilibrium position, the greater the restoring force. That's exactly where we're going with this. It gets really complicated because the force is changing, which means the acceleration is different all the time. And that's going to be tricky. Because you would think, everybody, that if I have a pendulum going back and forth, it's moving the fastest at the bottom, right? You would think that's where it experiences the greatest acceleration. Turns out the acceleration of the bob at the bottom is 0. It's just moving very fast at that point in time, but there's no net force acting on it. Whereas when the pendulum bob gets to the top, it's actually stopping momentarily, but the acceleration there will be the greatest. That doesn't ring true. Really, it seems like I'm saying something that's wrong, but if you've ever been on a ride at an exhibition or a fair or something, and the ride involves you changing direction, that's where you get rocked around the most. When you get to the outside and you change direction, that's where the acceleration is the greatest. Frequency, well, number of oscillations, number of oscillations per second. When we talked about frequency of circular motion, we said frequency was the number of revolutions per second. Well, simple harmonic motion is kind of any type of motion that's repetitive. So it includes circular motion, it includes pendula, it includes masses bobbing around on springs, it includes corks in water on a water wave, and this is measured in hertz. Period, well, we've already talked about that. It's the time per oscillation. And when we were studying circular motion, we said the period was the time for one complete revolution. Here it's the time for one complete oscillation. And of course the time, that period is measured in seconds. And the relationship that we learned in circular motion physics is the same as the relationship here. And just before we go on, I never really said it explicitly. Well, I think I did, but I'll repeat it. A complete oscillation is a complete back and forth. It's not from one side to the other for a pendulum. It's from one side to the other and back. It's not from the bottom of the mass's location to the top when it's on a bouncing spring. It's from the bottom to the top, back to the bottom. If you are in a boat and there's a water wave that goes by, you've ever been in a boat, you know that the boat goes up and down. The period of that wave is how long it takes you to go from the lowest point to the highest point, back down to the lowest point. Displacement. Well, this is, I'm going to use a word that maybe is not the best word, but for now I think it will do. It's the location relative to the equilibrium position. So we've talked a lot about springs and pendulums, and we've looked at them already. And again, you'll do lab work later on this week. But I'm going to switch gears and talk about a water wave. So this is the equilibrium position of a water wave, which means if I just leave the water alone, it's going to end up settling there. So when you talk about a water wave, this is what it looks like. And this is a snapshot in time. And I don't want to get too far afield of what we're talking about today. But briefly, a short period of time later, if you just look away and then you look back, you'll see the wave there. Are you with me? And again, without much thought, and certainly if you asked a small child, they will say that this point right here is actually moving left to right, won't they? But that's not what's happening. What's happening is that point is moving down while the point over here is moving up. And we'll study this in detail. But all that's happening is everything is bobbing up and down, giving us this illusion that something is traveling to the right. Something, by the way, is traveling to the right. It's energy. Okay? If we were to fill this room with Jell-O, we would get everybody out of the room first. Seal it, fill it with Jell-O, refrigerate it, and put a sheet of plywood on that side of the room in the corner and a sheet of plywood on this side of the room in the corner. And we had a pulley system, and I lowered myself down onto this sheet of plywood here, and you lowered yourself onto the other sheet of plywood, and I started kind of bobbing up and down on my plywood. You would end up bobbing up and down, wouldn't you? I would have transferred energy to you, but I didn't take a bucket of Jell-O and throw it at you. The Jell-O didn't move towards you. The Jell-O moved up and down, and the energy moved towards you. Okay? But what is displacement? Well, if you look at this piece of water, this would be the displacement. If you look at this piece of water, this would be the displacement. And tying on to what Noah said, and I'm glad you said it, it's all connected to force. That the force acting on this piece of the material is going to be greater than the force acting on this piece. Because the second piece is closer to the equilibrium position, there's not as much force needed to pull it there. That's an oversimplification, but amplitude is the maximum displacement. So, and you certainly don't need to draw all of these. If I had a mass on a spring, and this is the equilibrium position, and I set it into motion, so this is x equals 0, a displacement of 0. And I set it into motion, and it bobs down to here, and then it bobs up to here, That's the amplitude. That's the amplitude. And what we will discover is the amplitude is the same in either direction. That a pendulum goes just as far to the right as it goes to the left. The restoring force is what Noah was talking about. It's the force that is working to restore the state of affairs to the equilibrium position. So it's a force that I really want to avoid tries or wants to. The force that moves things back to the equilibrium position. And I'm not a big fan of abbreviation, but I think you get the point. So we're going to formally answer this in a second, so you don't need to write it down. But what's the nature of the restoring force for this spring that's oscillating up and down? Well, the force that the spring exerts on the mass and the force of gravity. Because when it's in this state right here, the force of gravity is primarily at work trying to move it back down. When it's at this state right here, it's the force that the spring exerts on the mass to try to pull it back up. Vertical springs are complicated in that way. Horizontal are easier to analyze. So before we get to two very quick examples, we've already talked about masses on the end of a pendulum and masses oscillating on the end of a spring. Those are the two types of simple harmonic motion that we will study in high school physics in detail. What is the nature of the restoring force on each oscillator? Well, the restoring force for a pendulum is related to the force due to gravity. It's not the force due to gravity. It's not the force due to gravity. And we will, again, an introductory lesson is always tricky for me because I always say we're going to study this in more detail later. But I want to give you a little taste of what we're talking about. If I have a pendulum and this is the equilibrium position, which means that maybe this is the amplitude, maximum displacement. The pendulum bob wants to get back to this state of affairs at the bottom. And right now, the force of gravity is acting downwards on it. And none of that force of gravity is pulling it back to that position because it's already in that position. Here, the force of gravity is the same value, but it wants to move in this direction at that point in time. So there is a part of the force of gravity here that is pulling it in that direction. And this would be the restoring force. And again, you don't need to draw this, you certainly don't need to write down many details here, but I hope you see that as it gets closer to the equilibrium position, the part of gravity that's trying to push it towards the equilibrium position gets smaller and smaller and smaller. So that's why I say it depends on the force of gravity. A mass on a spring, I'm going to just, to set things up for tomorrow, I'm just going to say it's a horizontally oscillating mass in a spring. It's a very ideal situation. We've got a mass that's on a frictionless surface. You can draw it. So we have a mass on a spring. It's frictionless. We've got a spring. And I take that mass and I push it in a little bit and I let it go and it just bounces back and forth. Here, the restoring force is the force that the spring exerts on the mass. Even though we are going to be doing a lab with a hanging spring, the lab we do will not be related to the restoring force because that's too complicated. A vertical spring has a restoring force that's always kind of a mixture of the force of gravity and the force that the spring exerts. Okay, before we do a couple of quick calculator questions, does anybody have any questions or comments? All right. What is the frequency of an automobile engine in which the pistons oscillate with a period of 0.0625 seconds? Well, if that's the period, then the frequency is the reciprocal of the period. And this is what I meant by a simple calculator question. You just need to calculate that. One divided by 0.0625. Missed my decimal. Hertz. Just barely idling, maybe. Maybe there's an engine problem at that point in time. I don't know enough about automotives. That might be a normal speed. It seems, or frequency. It seems kind of low. But I'm going to do some research. How many oscillations does the piston make in 3 minutes? This is a matter of a ratio. 16 hertz means 16 oscillations every 1 second. That's not right. "16 oscillations every second." You can put 16 cycles every second. You can put 16 movements every second. I just use oscillations. Equals X over, man, finding out how many seconds 3 minutes is child's play. So we need to multiply 180 by 16. And get 2880. Oscillations. The buzzer vibrates back and forth a total of 2.4 times 10 to the 5 times in 1 minute. What's the frequency and period? You know, these are problems you could have done in the last unit, except it was related to circular motion. The frequency will be the number of cycles. I'll use cycles this time. In 1 second. Well, that's pretty easy because it's 2.4 multiplied by 10 to the 5 cycles. So we're talking electronic buzzers. You hit something and it goes, nee. What's happening is there's something vibrating back and forth that many times per second, or per minute in this case. So we have to divide that by 60 seconds to get cycles per second, which is frequency. I want to say it's 4 times 10 to the 4, but I could be wrong. Ten to the 3? Okay. So that's the frequency. The period is 1 over the frequency. I'm not going to write down 1 over that. You take 1 divided by that and you get 2.5. See if I can get my exponent right this time. Times 10 to the negative 4 seconds. That's it. I mean, I could have taught you this lesson by giving you the definitions, doing these 2 examples. But I think trying to put it into context of things we're going to be working on is important for you. So there are some questions dealing with period, frequency, simple harmonic motion in your textbook for you to practice. I am also going to hand out your next written response assignment, which I will say is due in a week, Tuesday.